Hey everybody, this is Harbin. Welcome to video note 6.1 from Mole. So we're going to do 5 objectives in this video. Please make sure you're reading chapter 8 of your book, sections 8.1 through 8.4. So dimensional analysis is a technique that you can use to convert one unit into another. And so we're going to be using it in chemistry. So we need to try to make one unit go away so we can get a different unit to convert it to. So in order to use dimensional analysis, you need conversion factors. So we need true statements that are used as ratios to cancel units. So you might know that 1 dozen has 12 things in it, or that 1 spider has 8 legs, or that 1,000 milliliters equals 1 liter. We're going to use things like that to make the units go away. All right, so we have 4 years, and we want to know how many minutes that is. So we're going to change to red so we can see what we're doing. We're going to say, well, if I have 4 years and I want to know how many minutes that is, I'll use a conversion factor. How many years, how many days are in a year? Let's see. I know that 1 year is 365 days. All right, but that doesn't give me what I want. I want minutes. So given, find. All right, so days, let's see. So let's say days. I want to get rid of days, and I want to change days into minutes, but I don't know for sure, so I'm going to go to hours. And then I want to say, well, I know how many hours there are, how many minutes are in each hour. So I know that there's 24 hours in a day, and that there's 60 minutes in an hour. So using these conversion factors, I cancel out years, cancel out days, cancel out hours. Now I have to do the math. It says 4 times 365 times 24 times 60 gives me 2,102,400 minutes. Now, if you went to school for those 4 years every day, that's how many minutes you'd be in school. Okay. Metric conversions are the same kind of concept, but we're using metric units. So we want to change 4.65 kilograms, that's given, and find out how many grams that is. So we start with the given 4.56 kilograms times, well, I want to get rid of kilograms and change it to grams. And then I have to say to myself, what's bigger? I know a kilogram's bigger, and there's 1,000 grams in a kilogram. So I know there's 4,560 grams in 4.656 kilograms. What about milliliters to liters? So this is a volume unit. So given 9,500 milliliters, find liters. Okay, so start with my given 9,500 milliliters. And I want milliliters to go away, so I have to go to the bottom of my conversion factor and change it to liters. Then I have to say to myself, what's bigger? I know a liter is bigger than a milliliter, and I know there's 1,000 milliliters in a liter. Okay, so goodbye milliliters. Hello liters. 9.5 liters is what 9,500 milliliters is. Okay, so we convert it. Okay, these numbers don't change the amount you have, it just changes the unit. So, can you do this with more complicated ones? Yeah, you could have split units. So, believe it or not, I can run 3.25 meters in every second. So, all I did was take my given meters per second and write it as a fraction. Now, I want to find out how many kilometers per hour that is. So, I can only change one unit at a time. So, I want to change my seconds into hours. So right now seconds is on the bottom, so I want seconds to go on the top. And then I'm going to change seconds to minutes because I don't know, well I do, but I'm not going to use it. Minutes in an hour. So I mean seconds in an hour. And then I'll change my minutes to hours. And that'll take care of these bottom units and change seconds into hours on the bottom. But on the top I want to change meters into kilometers. So I'm going to put meters on the bottom and kilometers on the top. Okay. So let's just see what happens to our units. Goodbye seconds, top and bottom. Adios minutes, see you later. Nothing cancels hours, so I'm going to keep that one. Hours. But it's on the bottom. Okay, meters cancels meters. I know it's way over there, but it's still a chain calculation, and that's what happens. And we're going to be left with kilometers. So now we got to put in some numbers to make them true. 1 minute has 60 seconds. 60 minutes for every 1 hour, and that's our time units. And then kilometers, what's bigger? Our kilometer's bigger, and there's 1,000 meters in a kilometer. So then we do the math, 30.25 times 60 times 60 divided by 1,000, and we find out that I can run 11.7 kilometers in an hour. Believe it? Look it up. See if it's possible for me to do that. Okay. What about multiplied units? Well, okay, if we were measuring the dimensions of a room and we wanted to know how many centimeters squared it is, the area, so we have meters squared. Now, I don't know the relationship between meters squared and centimeters squared, but I know that meters has to cancel twice because it's multiplied twice. And I have to get centimeters squared, so I have to have them. So this one cancels the first meters, this one cancels the second meters, and I'm left with centimeters squared. So now all I have to do is make these true statements. What's bigger? Well, a meter is bigger than a centimeter. I know there's 100 centimeters in meters. Okay. So when I multiply that out, I get 121,000 centimeters cubed. Okay, it's called dimensional analysis. Use the units to guide you. So in Indiana, I buy a ream of paper. That's 500 pieces. Yeah, gross of bottle rockets. This is 144 bottle rockets. Woo, it's going to be a good day. And a dozen donuts. 12 donuts. All right. Why such large numbers? It's easier to count stuff in large groups if the stuff's small. So we use a mole in chemistry. And a mole is this many counted things. 6.02 times 10 to the 23rd. What? Yeah. Okay. You thought counting a ream of paper would be hard. Well, it's 500 pieces. Try counting a mole. All right. So why is this number so large? Because atoms are so small. And a mole is a really important thing because it lets us count really small things like atoms and molecules. And this number, 6.02 times 10 to the 23rd, it's called Avogadro's number. So what is a mole? A mole is a unit of measure, not just a furry animal. And this is moltato. And you might be saying to yourself, no, it's a potato. Well, here's its eye. And here's its little nose. Kind of looks like their little nose. And there's its smile. Oh, all it needs is its hand. Woo! There we go, moltato. The abbreviation for mole is MOL because you save a lot of time by not writing it. Okay, so how many are in 1 mole? How many molecules are in 1 mole of water? 6.02 times 10 to the 23rd, because molecules represent water. How many atoms are in a mole of helium? 6.02 times 10 to the 23rd. Why? Because atoms represent helium, and that's how much a mole is. How many pencils are in a mole of pencils? 6.02 times 10 to the 23rd, because pencils represent a pencil, a whole pencil. So if you had a mole of them, you would have Avogadro's number of them. Okay. Gases have an interesting feature. At standard temperature and pressure, 1 mole of any gas takes up 22.4 liters of space. How can that happen? Well, the particles are so small and gases are so spread out that you can have a mole of any gas at STP and they'll have the same amount of space. Okay, so here's 1 mole of xenon gas. How much? 22.4 liters. 1 mole of methane gas. How much? 22.4 liters. Okay, so STP we'll talk about eventually more, but it's conditions that are 1 atmosphere for pressure and 0 degrees for temperature. So here's 1 atmosphere at the temperature of 0 degrees Celsius. Okay, so that's how moles are related to counting. That's how moles are related to counting. Moles are related to volume. Now, how is mole related to mass? Well, the periodic table tells you how many grams are in 1 mole of each element. So you got to go get grams from the periodic table. The mass of 1 mole is called its molar mass, its atomic mass, its molecular weight, its molecular mass, all of those words. Okay. So, how much does 1 mole of carbon weigh? 1 mole of carbon weighs 12.01 grams. Okay. How did I get that? Look, there it is on the periodic table. I always use 2 decimal places. How much does 1 mole of carbon dioxide weigh? Well, I found out that 1 mole of carbon is 12.01 grams. 1 mole of oxygen is 16.00 grams, but there's 2 of them in there. So that 1 mole of carbon dioxide weighs 44.01 grams. Okay, where did I get these numbers? There's carbon and there's oxygen. And I used 2 decimal places so it's rounded. Okay, let's try another one. Aluminum oxalate, what? Okay, so 1 mole of aluminum is 26.98 grams, but guess what? There's 2 there. 1 mole of carbon is 12.01 grams, but there's 2 times 3, so there's 6 there. And then 1 mole of oxygen is 16. There's 4 times 3 is 12 of those there. Okay. So I have to add all that together, and I find out that 1 mole of aluminum oxalates is, okay, so this 16 times 12 is 196. No, sorry, 192. 12 times 6.0 is 72.06. And then this is 53.96. So we get a total of 318.2 decimal places, 02 grams is 1 mole of aluminum oxalate. Boom. Okay. So this is called molar mass, and it's mass of 1 mole. So here's what you have to remember about moles. 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd things. And those things can be atoms, molecules, or formula units, because that's what represents matter. Okay, 1 mole can equal 22.4 liters, and that's of any gas, only gas, at standard temperature and pressure. 1 mole also equals the mass in grams from the periodic table. So you can memorize the 2 numbers, but for grams, you have to use the periodic table. Okay. So use dimensional analysis to convert 12.5 grams of carbon dioxide into moles. So I'm going to say 12.5 grams of CO2. I want this to be moles, so I have to cancel out grams and get to moles. How do I know it's only 1 conversion? Because here's moles and grams right there. But this is all carbon dioxide this whole time, not changing its identity. 1 mole from the periodic table has a mass of 44.01 grams. How did I do that? I added up carbon plus oxygen. And then grams will cancel grams, and I'll be left with, you might have already guessed it because you got your calculators out, 0.28 moles of carbon dioxide. Okay. All right. What if I want to convert 19.9 moles of oxygen gas to grams? 19.9 moles of oxygen gas. Front row, O2. Moles and grams are related here. Moles and grams. Moles has to go on the bottom to cancel. Grams has to go on the top. And then we say 1 mole has, careful, is 16.00 times 2, 32.00 grams. All right, goodbye moles. Hello grams, 638 point, oops, just kidding. Who's kidding you? Me? 636.8 grams of oxygen gas. Okay. All right, similar, not simpler, similar questions. What if I had 3.59 moles of ammonia? Right. What do I want to find? Molecules. Okay, since molecules represent ammonia, I could say moles of ammonia turning into molecules of ammonia. And then I have to check my conversion factors. All right, this is moles and liters, moles and units, moles and molecules. Yeah. So I could say 1 mole has 6.02 times 10 to the 23rd molecules. So if I had 3.59 moles, I'd have 2.16 times 10 to the 24th molecules of ammonia. That's a heck of a lot of molecules of ammonia. All right. What else can we do? We can find how many moles, find out how many moles if we have liters. And we're assuming it's STP and helium's a gas. So 63.8 liters of helium times, let's say I want to get rid of liters, change it to moles. I know there's a direct link between moles and liters, but it's all helium all day. 1 mole has 22.4 liters. So goodbye liters of helium, little moles of helium. And we find out that there are 2.85 moles. All right, so those are mole conversions. What else can we use moles for? Well, here's some real world connections. Dogs love moles. Man, these are two of the cutest dogs ever. That's not real. I don't know what it is. So another use of moles is solutions. A solution is a homogeneous mixture, very, very, very well mixed. You could have solids mixed together, solids and liquids, liquids and liquids, gases and liquids. Two parts of a solution are the solute and the solvent. So if you mix two liquids like water and vinegar, it's called miscible. Okay. Solid and liquid makes Kool-Aid. Solid and liquid makes salt water. Liquid and liquid makes food colored water. Okay. So time to concentrate. A solution is a solute plus a solvent. So a concentration describes how much solute is in the solution. Okay. So if I have this much and then I look at these, I'm trying to figure out how much of this solute is in the total solution. And I'm going to get concentration. Okay, so the chemist's most popular way to describe concentration is molarity. So molarity is concentration. Molarity is concentration. So what's molarity? Concentration expressed in moles of solute, because we want to know how much stuff is dissolved, in liters of solution. So we want to describe the solution's molarity. And the units for that are going to be mole per liter, or you can use the capital M, which we've seen. They both mean molarity. So what does 5 molar HCl mean? This means 5, I'll write it out, 5 molar hydrochloric acid. It means there's 5 moles of HCl in every 1 liter of solution. That's what molarity means. So moles per liter. Yay, finally we get to know what it means. Here we go. What is the molarity of 2.5 liters of solution that was made with 45 grams of NaCl? What? So we want to know the concentration in molarity. So find capital M. Okay, given 2.5 liters and 55 grams. This is a solute and this is solution. Okay, so let's see how to solve this problem. Well, I'm going to start with the 45 grams of NaCl, because that's my solute, but molarity has to have moles. So I'm going to change grams of NaCl to moles of NaCl. And I find out 1 mole, and I go get from the periodic table 22.99 and 35.45. Find out 58.44 grams of NaCl is in a mole. And that'll give me moles, but concentration is moles per liter. Okay. And so I also need liters here. Oops, let me just get moles from this one. I'll get moles and I'll find out it's 0.77 moles. I'm just slowing it down a little, taking a step back, stopping right there. So that's how many moles of solute. But I want the concentration, I want the molarity, so I have to say, well, 0.77 moles of NaCl is in the 2.5 liters of solution. Okay. So the molarity is 0.31 molar, which means 0.31 moles per liter of NaCl. Okay, one more. How many grams of NaCl? So 5 grams of NaCl must be dissolved to make given 25 milliliters of 3.5 molar solution. Okay, 3.5 molar means 3.5 moles of solution for every 1 liter. Moles of solute for every 1 liter. Okay, so let's take our 25 milliliters. And you know what? This means liters, so we have to change milliliters to liters. Milliliters to liters. Okay, so I'm going to say 1,000 milliliters for every liter. All right, now that I have liters, I can use molarity as a conversion factor. I know that for every 1 liter, there's going to be 3.5 moles of solute, which is calcium chloride. But I'm not done until I have grams. I'm going to use one more step. Love dimensional analysis. For every mole of calcium chloride, how many grams of calcium chloride are there? Okay, well, number 1, moles. Where do I go get the grams from? The periodic table. So I had 40.08 and then 35.45 times 2. Where did I get those? Periodic table. Boom. Yeah. 110.98 grams. Okay. So by milliliters, see you later liters, but by moles. And guess what we're left with? We're left with grams of calcium chloride. So in order to make this solution, I'm going to have to take 9.71 grams of calcium chloride, dissolve it in enough water to make 25 milliliters of solution. So to review, moles are groups of particles or anything that contain Avogadro's number of representative things. Molar mass, you got to go to the periodic table. You got to memorize what a mole means, what it equals. Only use 22.4 liters for gas and STP. Hey, dimensional analysis solves problems. Okay? And then molarity is concentration of solutions, and we can use that too. Read your book and see if you know that stuff. And that was long. Welcome back. Peace out.